Okay. In the last class, we learned how to model a normal beam or normal frame with a beam and with plates. Now let's understand how to do a lifting analysis for this particular structure. So when we do the lifting analysis, we need to be clear like what we are going to intend. So I am going to perform a lifting analysis with 4 slings attached to one hook point. So for that, I need to model my hook point. The easy way is like, let's say I want to take it from this one. So when we look at the So when we look at any lifting, what happens is, let's say I have a frame or something to lift. So we may directly model a sling like this. So we may directly model a sling like this. But we can ignore the connecting point. So most of the time there will be a pad eye. So we need to account for the pad eye as well. So what I always suggest is you need to model that pad eye part again. So from this center point, you need to have a member to account for a dummy member to account for the pad eye. Then from this pad eye, you can connect the slings to the hook point. Okay. You can connect this link to the hook point. So first we are going to model this dummy member for the padding. Then we need to have hook point. So when we come to the hook point, one thing we need to be very clear about is it's regarding the horizontal angle this sling makes with the horizontal plane. So this angle should be minimum 60 degree. It should be minimum 60 degree, so that we need to maintain. So first what I will do, I will create 2 members. So one for the pad eye, so it will be a dummy member, and another one for the sling. Okay, another one for the sling. So for that, what I would do, I will come over to my model, and first I will create the property for the pad eye. So for that, what I would do, I will come to, so I will put like pad, and so I can give, so it's a dummy number, I don't care much about the size of it. So let's say 4 centimeters, I will give 5 centimeter. We can change it once. If it's failing, we can change it later. So, and I will give a thickness of 2 centimeter. So it will be like a, so I will make the density 0.0001. I will change the material property to 35.5. And I will click, so maybe I can change the color so that I can have a easy visualization. Okay. Next one, I will define my sling, SLG. So defining the sling, I need to be very careful. So I can go for ODNT. So this one also I can select one particular, maybe I will go for 6 centimeter outside diameter and thickness of 2.5. So this one doesn't much care much about, because when we do the SACS analysis, we only care about is how much tension coming onto the slings. If you want, you can give the actual property of the sling if you have. Otherwise, you can keep it. But the important part is you need to make this one as a gap element. So I will explain what is gap element. So gap element have some certain features which will enable us to model it in a different way, whether it's a compression only member or a tension only member. Because if you take the sling, it will only take the load when it is in tension, and if you take some stopper or something, it will transfer the load only when in compression. That I will do a separate video. So for this one, I want to make it as a gap element as a tension only member. So I am going for the global control. I will go to miscellaneous, and I can make it activate gap element, and from here I can select tension and click apply. So I have these two things ready. So first I will create the thing for pad I. So at the moment, let's see what is my section of this one. Okay, so this one is like 41.91. So the half is approximately 21 centimeters. So from there for pad I will give some 100 centimeters extra. So for that, sorry, 10 centimeters extra. So for that, what I will create a joint over here. Go to here, pad 1, and it is at centimeters. Maybe I can round it off to 32, 32 centimeters from here. I am not giving any fixities for this particular joint. So this is pad 1. So let me see visually how it looks like. So I can select pad. Okay, looks good. So I will give it everywhere. So this is pad 2, this is pad 3, and this is pad 4. So let me make the joints. Now I want to create the hook point. So while creating the hook point, first we need to understand about our weights. Now here we have only the self weight. So first let us give the self weight and see what is our COG coming in XY plane. So for that, what I would do, let me hide our pad. So for that I will come over here in the load, self weight. So I'm giving a self weight like self ID. Maybe I can put 001 or something. I'll go to add existing load. So this is my sum of forces, and this is my x and y. So my x is coming at 5.34. Let me take a screenshot so that. So and y is at 5. So for that, what I can do, I can come over here. I can activate this plane. So let me see. Let me give this one again. Okay, I think it's in 001. Let me see whether this load property gave it's in STLMT because I didn't apply it. So for that, add to existing. Maybe I will, for a confirmation, I will use delete existing as well. Okay, good. Now let me bring back my pad and here I want to create a plane. So for that, I would do come to here, 3 joints. I will select one joint, second joint, and third joint. So it will take a plane from this particular axis. So here I want to create a joint, so it should be minimum 60 degree. So for that I can have two options. So what I can do is I can take this angle. So what I'm gonna do is I will come relative to line angle. So first understand what is my distance. So if it's 60 degree, that is should be equilateral triangle, right? So let's see. So for that fixity, I can put it fixed. Relative joint A, relative joint B, and angle defining the plane. This one. So I will go for minus 60. Baseline length I am putting 0. Intersection length I will put this one. So baseline length and intersection length, you can refer to my previous video where I am explaining the baseline length and intersection length. I will put it over the corner, you can refer. So let me click apply. pad I5 has been added also. Let me see. So if I okay, 1 minute. It will be there because when I hidden these members, I didn't show this point. Okay, so you can check the ankle. So let me change the name of the joint for easy understanding. I will make it hook. Okay, so we can check the angle. So come over here, first one, second one, third one, 60. First one, second one, third one, 60. So it is 60 everywhere. So you can check with anywhere because it's also 60. This is also 60. Okay, so now I can connect my slings from here. So for that I will come over here. I can select my sling group SLG from and immediately to pad 1, pad 2, then to pad 3 and to pad 4. Okay, so this is how our sling looks like. And now I want to give some releases, because when we think about sling, it will not transfer moments, it will only transfer the translational forces. So I want to give some releases. So the release what we usually provide is, we can come over here and select these ones. So a release, so a release joint will be here at the top. So here we used to provide 00 00 11, and here we provide 000 111. So you may ask why we didn't release the MX over here, because there is an understanding there can be some sort of, if we release all the moments, the equation will not solve. It will create some instability in the equation solving. So for that, once we give at the hook point, we keep the MX, but in reality, since here we release, it should not transfer. There will not be any moment transfer. We can look at the result as well. So here if I look, this is the one. So here either member type, you can again give a local modification, or the previous one will be fine. If you want, you can give. So similarly I need to do for everything. So 000 000 sorry 00 00 11 and 000 111 and touch. Okay, so now I give my properties. So second thing is like, first thing, if you look, we gave the boundary condition over here. Maybe let me increase the size. Then we gave our member releases as well. Now once we give this one, next one is we need to give the load combinations. So when we talk about the factors, let's understand what are the factors involved. So let's say we have few factors. So one is weight contingency factor 1.1. Then next one is DAF factor. I am going for a subsea thing, and if the idea goes down, is like DAF will come into 2. Then consequence factor of 1.3, let's COG shift factor of 1.05, and this Q factor of 1.5. So it goes like this, but I don't want to use DNV at the moment. What we will do is we will directly use ANSYS, sorry, API. So in the API, we have only two factors. So one is 2, which is very critical towards the lifting points, and another one is 1.3, which is for the non-critical members. So if I want to use the API factors, what I can do is I can come over here. I will create two load combinations. One is LC1. So that is taking care of AP factor of load factor of 1.3, and another one is LC2. It will be taking care of 2. So I'm using only two simple factors as per API. And then here what I can do is, before running the analysis, we need to give the spring constants. That is very critical. Now thinking about the spring constants, how to provide it. So for that, what I would do, I will come over here in XY plane. I will just create the XY plane. Okay. So the idea about giving this spring constant is we have explained in the last class. So we have two options to give the spring constants. So either we can provide xy over here at any diagonal corners, or what you can do is you can provide only stiffness for x, here only for y, and at this corners for x and y. So I think this one is more common with the very experienced engineers, and this one also I have seen. So I cannot give a judgment which is more correct or wrong, both, but both will serve the purpose. So you can select anyone, but I will go for the green type. So for that, what I would do, I will come to the join, take the spring, and here I will provide 10 kilonewton per meter, apply, and here I will provide 10, 10, apply, and here I can provide y, 10 kilonewton per meter, apply. So now once I have this one, let's see how our total system looks like. So this is how our fixities and the member list looks like. There is one important thing we need to do. So that is, we need to give the effective length. So if you look at the effective length, that is very important. So I will take the BM1 and just the pad eyes. Rest of the things I don't want to see at the moment. Okay, plate also I need to hide. Okay, so if I look over here, so this beam is simply supported between these two pad eyes. Similarly with this beam, and this beam, and similarly for Z as well. So to give the effective length, what I will do, I will come over here, and in the property I can go to effective length. I can take L by LZ, and here I can put a length factor 1, and I can select these beams. So since it's a square shaped, I can select like this. So if you look, this is effective length 10. So similarly for all the beams, it is the case. So what I can do, I can select all these beams. I think here the two beams are there. So I need to delete one extra beam. So if you look, there are two beams. So I will need to delete the extra beam. So for that, what I would do, I will come over, delete this. Okay. So I think it's select. Okay, that one got deleted. So I think my COG values, I need to check it right now. We may have missed something. So okay, so now let me give this one. Okay, so now coming to this diagonal beams, we need to take a decision which one is through and which one is getting splitted. So I am assuming that this diagonal is through member. So for that, what I would do, I will come to property effective length. So for Ly, that means the Ly and LZ is defined as per the local axis of this one. So if you look, this is the local axis. So this is the bending about the y-axis. So when this beam bent about y-axis, there is no support getting supported. But when it's bent about z-axis, it is supported by these two. So what I can do, I can select only Ly, and I can put the effective length as 1, and I can select these beams. Now for okay. Now what I can do, I can give it for LZ. So LZ, everything will be common. So I can see this Ly and LZ values. Ly. So I can see the Ly values. Then LZ values as well I can see. Okay, I have given everything. So now let me revisit my loads. So for that, what I would do, I will come to group, show only the beams and the plates which I need to provide the weight, and I can go to load, self weight, and here basic. Okay, so delete existing load. Okay, now this one become correct, like x is 5 and y is 5. So we can check. I think we've created the hook point correctly, but the load was having some issue. So we can check the hook point as well. So when we look at the hook point, x5, y5. Okay, so that one is correct. So earlier I made a mistake, sorry. So this is how we need to set up our model. And we can do one more thing. If you want to see only the final load cases, you can come to option, the load condition selection. You can select only these two loads and click apply. Then let me save this one. It's demo 5. Now to run the analysis, what I can do, I can come over here. I can select static. In static elements with gap elements, because we are using a gap element, and I can select my element check option. I will go for the default one, and then SACS model file. I can select the SACS model file. Then what I can do is I can change the output naming demo file, and here I can run the analysis. Okay, it got run. So if we click on this one, you can see the results. You can check for the maximum combined UC. So the maximum UC is very less. Okay, our pad eyes are failing. We need to update that. Our slings are good. So pad eyes we need have some updation, because I always, even the pad eye we don't care much, but I always prefer the pad eyes also should be passing in our normal checks. And then if you look, the UCs are very less. And if you want to see the plate UC, you can always come and check over here. So it will show the plate UC. So the maximum plate UC is only 0.3149. And if you want to see the sling forces, maximum sling forces, you can come over tension internal load. Okay, so this one is showing in newtons. That's why this is showing like this. If you want to see, you can always come and see member and forces in table. I can select. So you can see the member and forces. So these are the member and forces on these slings for this particular loads. So this is how you do the uh, lifting analysis. And you can do one more thing. You can see whether our joint reactions are, so joint spring reacts. Maybe I'll go for joint reaction. I can select these joints where we give the springs. So ideally their spring reaction should be very minimal. Then only we can say our, so see, there is no much reaction. That means our lifting analysis is good. Even you can check your spring reactions over here. Reaction force X. So this reaction force X totally is 0. Reaction force Y totally is 0. And the reaction force Z should be equal to our load. So it is our LC2 case. Now if you want to see for LC1 case, you can see for LC1 case as well. So this also you can come and select joint reaction. So hook point a joint reaction for LC1 and for LC2. Now the next thing, you can see the deflection plot. So for the deflection option, you come over here. You can see for LC2. If you want to see the dash, how the deflection acts, if you want to see the animation, you can use this one and see the animation. So this is exaggerated view. So with the shape factor, you can maybe delete and see. If you want to see the actual deflection, you can come over joint displacement total. You can see what is the actual displacement. So this is how you do a normal lifting analysis. Thank you.